Good. Okay, so let's start. So today we're going to continue with this thread, the final thread, which is this hardness versus randomness. And what we are heading towards is to somehow show that the Nissan-Wigderson conclusion that if there is a hard to guess function, then P equals BPP. We want to make the same conclusion even when you have just a function that's hard to compute. In the sense that you're just given the guarantee that every circuit makes a mistake at least one place. And we want to use that to build the Pseudorandomness indicators. And we were talking about a rough roadmap last time, which is to slowly try and weaken the assumption on what f is. And the way we're going to do is we're going to start with a function with a very weak assumption and then get another function with a slightly stronger assumption. And hopefully, after a few iterations of this process, we'll now get a function that we can use to apply the Nissan-Wigderson generator on. At least this was how the original proof of Nissan-Wigderson was, whereas we are going to try and do it in one shot. But I think perhaps the part of this proof that may be the most surprising is the fact that you can go from worst case hardness to some average case hardness. I mean, in some sense, it feels like going from an average case hardness that looks like every circuit makes a mistake at 10% of the places to every circuit that makes a mistake at, 49% of the places. It somehow feels a little more believable. Just because you've seen randomized algorithms and you've seen this sort of error reduction type steps, it feels like maybe you can do some version of this. And in fact, this was the original intuition also. There was a notion of something called the direct product theorem or Yau's XOR lemma, which was basically tailored towards this, though I'm not going down that road at all. But perhaps the most surprising thing is the fact that from the fact that you are making one mistake to somehow spread that mistake into a constant fraction of the places, that feels like a rather powerful thing to say. So today's lecture, the goal is to just do that. Like by the end of the lecture, what I want to do is start from a worst case hard function and get a function that has some average case hardness. It's not going to be like half minus epsilon, which is what we eventually want to apply in Nissan-Wigderson, but nevertheless we'll get something. Okay. Okay. So now let's go over the thing. So we had this multiple notions of hardness, which each one weaker than the previous one. So the strongest notion was this notion of saying that it is hard to guess. Again, I'm not really writing it, but you have a particular circuit size in mind. And everything here that I'm stating here is with respect to that circuit size. Okay. So epsilon hard to guess is like saying that no matter what circuit you take of the requisite size, the chance that your circuit computes the function correctly is at most half plus epsilon. Okay. And because this is true for all circuits of a certain size, it's also at least half minus epsilon. So it's basically saying that you aren't doing significantly different from random guess. Okay. Then the weaker notion that we had was this hard to approximate. And we will just say that some function is epsilon hard to approximate to just mean that no matter what circuit you write, it will make a mistake on some epsilon fraction of the places. Okay, so that's what hard to approximate means. And worst case, I mean, if you were to write it in terms of probability, this is like saying that the problem for every circuit, the chance that you get it right is at most 1. It's like strictly smaller than 1. This is just a different way of saying that it must make a mistake somewhere. Okay. And one of the things that we are trying to eventually plug our hard function into is the Nissan-Wigderson theorem, which stated the following, that if you are given, I should have written that, if you are given a family like this that is in exponential time, that is, you have some upper bound for the family. Okay. And you know that it is like hard for size sk, that is the function, the here function is hard for size s of k. Then it tells you that BCP is in time t of n, where t of n is this weird quantity. Like you compute the inverse of this size function, take the square of it and divide by log, blah, blah, blah. But I'm really going to just be focusing on the special case when sk is 2 to the delta n. Okay. In that case, t of n is going to be order log n. And therefore, the conclusion is basically saying that BPP equals p. So throughout the rest of today's lecture and the next lecture, we will be focusing on the hard function that is given to us having something like this much hardness. And we don't really care about it. Basically, the point is if I see polynomial factors being added, I won't worry too much about it because I'll tell myself, oh, no, my hardness is like exponential. And these poly factors, etc., don't hurt me. Just that if S is much smaller, you will have to be a little bit careful about, what sort of factors show up. But I'm going to work with 2 to the delta n so that, polynomial factors that will add up in the process are not going to hurt me. Okay. So this is what we are eventually going to try and plug things into. Okay. So what was the plan of building PRGs? So the main plan was the following, which is we are given some function f which is on k bits. And I can equivalently think of this as some string of length capital K, where capital K is refers to 2 to the small k. Okay, this is the truth table of this function. And the plan is to basically apply some suitable error correcting code. We do some encoding, using some error correcting code. And as a result, this k bit string will now become some k prime bits, where k prime is much larger. Okay. Hopefully, I don't want it to be too much larger, but this is what will end up happening. And this also, I'm going to interpret this as some function on 0, 1 to the k prime, where k prime is like log of capital K prime. Well, it might be the case that you will have to ignore, you'll have to pad up the string so that it becomes a power of 2 so that you can take logs correctly, etc. But those are details that don't really matter. Okay. And last time we roughly convinced ourselves that there was some notion of local decodability that we wanted for this error correcting code in order for it to be useful for this hardness amplification business. Okay. And so let's just recall what the local decodability was. By the way, since we have seen this earlier, rather than talking about circuits, let's just talk about randomized algorithms. So on every input, a circuit is supposed to compute an answer, but I will normally be okay if the circuit gets this, or the randomized algorithm gets it right with probability 2/3 on every input. There is a generic way to convert this to a circuit, but I'm just not going into it at the moment. Okay, what is a local decoder? A local decoder is basically an algorithm that has the following guarantee. Okay, suppose f prime is a legitimate code word. Okay, it is the encoding of the function f. Okay, but on the other hand, you don't have access to f prime. What you have access to is g, with just the promise that g and f prime actually agree on a lot of places, in the sense that they disagree on at most delta fraction of places. Okay, that's the guarantee on g, and the decoder has access to g. It doesn't have access to f prime. But what the decoder wants to do is maybe compute, I don't know, one specific value here. Okay, that's what the decoder is trying to do. It's given a particular input x, and it wants to know what is f's value at x. Okay, so let me just, okay, so this is where x is, and I want to know what is f's value at x. And in order to do this, what this decoder is going to do is it's going to query g at a few points, maybe at this point, and this point. It's going to query g at a bunch of places, and based on the values it sees at those places, it returns a potential value for f of x. So obviously the choice of the locations that the decoder is going to check, etc., maybe no, decoder is some randomized process. It's going to decide on some locations to choose. So what we want is, like, based on the randomness of the decoder, on every input x, I want the decoder to correctly compute the value of f at x with probability at least 2/3. Okay. So such a thing is called a local decoder. A local decoder is basically, it's called local because the definition is set up in such a way that you can imagine local decoders that don't even look at the entire string f prime. It is only going to make a small number of queries because it's only interested in one coordinate of f. So why should it? I mean, potentially that is something that you can get from looking at a few coordinates. Okay. So so what did we see? The observation that we had last time is just written this down. It's like saying that if you have a local decoder that has certain properties, then you have certain hardness sort of transformations. Okay, let's just pass this statement. So it says that suppose C prime is some circuit of size S prime that apparently approximates the encoded function f prime with error less than delta. That is, it gets f prime right with probability more than 1 times delta. Okay, so that's the same thing as saying that if I look at the truth tables of C prime and F prime, they differ at fewer than delta locations, delta fractional locations. So what I can do is I can now define my new circuit or my new randomized algorithm to be the following. It takes this old circuit C prime as an oracle. That is the received word it is getting. And it just applies the decoder using this circuit as oracle. So whenever the decoder says, hey, I want the value of whatever G at a specific point, at that point it evaluates the circuit and then says, okay, this is the value of this. And the decoder, once it gets the values of C prime, is apparently supposed to correctly compute the value of F with probability at least 2 times. Okay, so this is just written this down as an observation. The only thing to keep in mind is that if you have some guarantee on the size of C prime, the new circuit you built right now is a little larger than C prime. Namely, it is the old circuit, the C prime size, times whatever time the decoder took. If the decoder made 7 queries, then you're like running the circuit C prime 7 times. Okay, so that's why I put it as it's like the size is at most S prime time, whatever is the time taken for the decoder. Okay, so the contrapositive of this would be the following. If you know for a fact that the function f cannot be computed by circuits of this much size, then there could not have been a circuit that gets some guarantee like this with size at most s prime. So when you do the hardness amplification, in some sense, the size guarantee reduces a little bit because the proof goes in the other direction. And you are like adding more stuff to the purported circuit there and to get a circuit here. So the size degrades a little bit. But this is where I'm going to say that, look, as long as you tell me that T dec is very small, I am dealing with exponential hardness, so this is not going to work. Okay, so that's where all of those is going to come. Okay, yeah.
You suppose F is hard for worst case, right?
Yeah.
Now we will design a circuit for it like
probability 2/3.
Yes.
But this is, so I'm just going to use some complexity jargon. But you know that BPP is in P by poly. So anything that can be done by a BPP algorithm can be done by a small size circuit. So since I'm constructing a BPP algorithm for F, this also implies that there is a small circuit that does the same thing. So basically what you'll have to do is you'll have to reduce the error to smaller than 1 by 2 power the input length. And then you will know there is one random choice that will just work for all inputs. So this is the standard Edelman trick. Okay, I can get to this towards the end. Okay. So therefore, you would really like an encoding function to have the following properties. I'm going to list down the properties and list down exactly why we need each one of them. Okay. So the first property we want is that I want the code to have decent rate. I don't want K prime to be significantly larger than K. Now, why is that? Now, what would go wrong if I had K prime to be much larger than K? So basically, this quantity, whatever this is basically going to play the role of the size S, which is the whatever. That is, if you assume that something is sort of average case hard for size S, then it is worst case hard for size S prime. Sorry, I turned it the other way. Sorry, if it is worst case hard for size S, then it's average case hard for size S prime. Okay. The thing that I have not written is that S and S prime are really just functions of the corresponding arities.
Yeah, okay.
Like it could be the case that, it could be the case that this, whatever you have here, is actually, exponential in, or rather, let me say, suppose this S that you're dealing with, that was exponential in K. But now I'll have to divide by t dec, and then now I get some new s prime. But if k prime was way larger, what used to be exponential with respect to k need not be exponential with respect to k prime. So I want to sort of say that the function roughly, whatever hardness you had with respect to k, continues to hold with respect to k prime. That is, this doesn't degrade too much, because I've made arity a little larger. So that is why. So the first thing. So that is with respect to the t dec being small. That is also because I don't want s prime and s to be different. And I want the other reason for k and k prime to be roughly similar is because eventually the generator is supposed to compute this encoding. As a part of the generator, you'll have to start with an f, compute the encoding, and then plug that into NWB. So this is computation you're going to do. And if this is too expensive, this is going to hurt you a lot, not just with respect to the trade-off between what s is as a function of k and versus k prime. Also with respect to how much time you're going to take to run the encoding. Okay. And then finally, I would ideally like this delta that I'm working with above to look like half minus epsilon. Because then I can directly plug it into Nissan integers, because that's what I'm trying to get to. Okay, so this is just saying that so that if this is the delta, then we truly have a function that's not this half. It's not. At this point, you should instead be saying it is epsilon hard to approximate, like epsilon hard to guess, because it's like very, very close to random guessing. Okay, so this is what we are trying to get to. And last time what we saw was that Hadamard codes were something like a quarter minus epsilon locally. Okay, that we came up with a decoding algorithm. And in fact, the decoding algorithm was this very simple, basically, character that you could have. If you want to decode the ith bit, what you do is you just query the Hadamard code at a random point v. And then also query it at a random point, the point v plus ei, where you just flip the ith coordinate. And the XOR of these two things is supposed to be the value of the inner product. And there was a half minus epsilon chance that with probability at least half plus epsilon, both of them were actually uncorrupted locations. And so we could do some Chernoff bound on top of this. And that was the Hadamard decoder. So we could have used this above, except that this is terrible. I mean, the code is of terrible rate. So we don't want to use Hadamard codes. So what we are going to be doing is we're going to ask, are there like good rate codes that are actually locally decoded? Okay, and what we are going to do before we go into this, I'm going to talk about a slight modification, which at the moment will feel, I don't know, you could either take it, I mean, when I saw this modification for the first time, I thought it was not a big deal. But then later on, I was like, no, this is what makes all the difference. But then later we will see that we can actually get this modification, so it's not a big deal. So I'll just give you the modification and let's see. I would like to see what you people think about this. So with respect to a local decoder, what is the ask that you have? You have some initial message, and this message got encoded into some long string. And now let's imagine that someone gave you a corrupted version of this long string. So what is the ask of a local decoder? The local decoder says, look, I am interested in this coordinate. Okay. And for this, what the local decoder does is, in that case, I will query this, and this, and use some randomized algorithm to tell you what that coordinate is. I'm going to modify things a little bit and instead ask for something called a local character. Okay. Where the ask is not a message coordinate, but it's actually a code word coordinate. That is, I am given a corrupted code word. So the particular position I'm going to ask, maybe that is one of the corruptions. But I want to know, had it not been corrupted, what would the value there have been? Okay. And again, the algorithm is going to query a whole bunch of random locations and then decide, had it not been corrupted, the value would have been blah. Okay. And that's what I'm going to call a local character. So basically, the difference is that this corrects code word coordinates, and this is like, okay, I don't want to use the same verb. I'll say decodes message coordinates. Okay. Now, what we really want is a local decoder. For the application we are talking about, because we had a certain function, we were interested in the value at a specific point. We don't care about what the encoded function's value at a certain point is. I want this function. So we truly just want the local decoder. But it will be easier to construct local characters. Okay. And we will see that, the sort of codes we are interested in, local characters are actually good enough. So to convince you as to why local characters are perhaps good enough, let's go back to the Hadamard code itself. And Hadamard code previously, the decoder is going to give a single coordinate of the message and ask you, can you tell me what the value is supposed to be for the encoded function? I mean, what the value is supposed to be in the character, the thing based on the character encoding. But suppose instead of this, I had given you, I had asked you, I want the decoded message, but I'm interested in the character code word location at U. What would you have done? You would have just done again query V at random, and instead of EI, you will replace this with U plus V. And you will do exactly the same thing. Right? I'm going. So let's say, so U comma V is supposed to be, this is supposed to be the inner product of whatever X and U. I don't know what X is. I'm trying to figure out what the inner product of X U is. So what do? You basically say, let me query the inner product of X and V and the inner product of X and U plus V. And if I add these two, I'm supposed to get inner product of X and U. The same analysis will tell me that if I'm within quarter minus epsilon, then the chance that both of them are correct is like at least half plus epsilon, or half plus 2 epsilon or something. So you can do a Chernow bound type. So in fact, Hadamard code was actually locally correctable. It was not just locally decodable. Okay, you could actually correct any message coordinate, sorry, any code word coordinate also. In fact, this was a Hadamard code is a situation where the message actually shows up in the code word itself. If I start off with x1 through xn, the corresponding inner products with respect to e1 through en, well, x is just sitting there. So I might as well imagine that I was actually correcting the coordinate corresponding to ei, which is the same thing as decoding with respect to the coordinate I. Okay, so this minor modification, the way we will eventually fix it is like we will eventually fix this difference by what is called a systematic encoding. By which what we mean is we will always construct codes such that the message shows up in the code. So it is actually convenient to just work with locally correctable codes because it's easier to come up with correction algorithms. Okay, anyway, we will deal with this towards the end of today's lecture, but I'm just pointing out the difference that's happening. Okay, so what we are going to do is, this is the code that will eventually give us what we want, which is the Reed-Muller codes, which we briefly talked about previously. And I'm going to, we'll show that this is actually locally correctable. Okay, so what is a Reed-Muller code? Well, you're working over some alphabet Q, so there is some field of finite field of size Q. So that's the underlying alphabet. And there's usually two parameters. One is the number of variables and the other is the degree. Okay, and you interpret the polynomial as something in x1 to xm whose degree is at most d. And typically this d is like much smaller than q and stuff like that. Okay, so the degree is at most d. And what is the encoding? You basically just evaluate this polynomial at every point in the domain. So it's an m-variate polynomial over SQ. So you can potentially evaluate it on all points in Q power n, and that's the encoding. So the encoding is this giant tuple of Q power m field elements. Okay, and So Schwartz-Zippel will basically tell you the distance. This is at most d over q. Or maybe I'm missing which 1 minus d over q, I guess. Yeah, 1 minus d over q. Because two different code words can agree on at most d over q coordinates. So therefore, they must disagree on at least one of these things. And this is the part where I'm assuming that d is much smaller than q, so that I can apply Schwartz-Zippel. Okay. Let's not worry about rate and so on right now, because eventually we will set parameters and then we will see what happens. So this is the main theorem I want to show. Okay. There's some, you assume that q is large enough. Let's say 36 is what at least my proof, proof in Vadan's notes gives. And I'm also going to assume that d is like significantly smaller than q in the sense that it's at most q over 9. So that I have some distance, okay, in this code. And I want to say that I can get a 1 by 12 like local character. I didn't define local character, but you know what it means. It's some algorithm that is given a particular code word coordinate, makes a bunch of random queries on a corrupted code word, and figures out what the correct code word coordinate is supposed to be. Okay, so we have a local character that we will build, and this local character will actually run in polynomial time in the parameter set. Notice that the block length of this code word is like q power n. It's huge. Whereas this local algorithm is only going to run in time poly in q command. Okay, and for in fact our q will be very small that we'll eventually assign. So both q and etc. So is the theorem statement clear and what we are going to try and do? Okay, cool. So let me try and pictorially tell you what this algorithm is going to do. Okay, so I can only draw things in 3D. So this is, imagine that you're dealing with an ambient dimension of 3, that is m is 3. And this is just a cartoon of fq to the 3. Okay, so there was some polynomial. So maybe, so whatever, f is the actual polynomial. Okay, but what I have access to is, I don't know, some g, which is from fq to the n to fq, such that delta of g and f is at most 1 by 12. That is, g is this corrupted version. That is, it just happens to agree with f at many places, potentially disagrees with f at some, I don't know, delta by, sorry, 1 by 12 places. Okay, so the places where it disagrees, I don't know where it's going to be. It's going to be some bunch of points. Right? It's like some locations in this picture where it could potentially disagree. Now, you are interested in figuring out, I am giving you a particular x. And you want to know, in the correct encoding of f, you would have taken a specific value at x. I want to know what is that value supposed to be. Okay, in the correct thing, what is it supposed to be? So how do I do this decoding in a local fashion? And this is an idea that is pervasive. I mean, like it's used so much here when you're dealing with like Reed-Muller codes and local properties, etc. And the plan is the following. Let's just shoot a random line in the space passing through x. Okay. And what I'm going to do is I'm going to query all of these points. Now let's just imagine that there was no error. Okay, there was no error at all. What would you expect to see on those points? So that is if g was equal to f in that case. Then on that line, you should see a univariate degree D polynomial that agrees with the values there. Because what is that? What is the value that it takes here? Well, the value is f evaluated at that point. This is f evaluated at this point, etc., etc. So if you just look at f's restriction on that line, that is also a degree D polynomial, which is basically explaining what is happening on that line. So what you should be seeing is some univariate polynomials restriction on that line. Okay, so why not do the following? Let's just decode that univariate polynomial, because some of those things would have been corrupted. Because maybe some of them pass through these gray clouds, etc. We will decode that univariate polynomial and answer according to whatever that univariate polynomial claims the value at x should be. Okay, and that's the algorithm. So the algorithm is just the following. So you are given a particular input x, and you want to know what is the value that the correct f is supposed to take at x. And what do? You just choose a uniformly random direction. I'll call that u. Okay, and look at the line passing through x in direction u. So as an equation, this is what it will be. I mean, this is L of t is basically x plus t times u. Okay, or as a set of points, these are the q points that correspond to this line. Okay. Now what I'm going to do is I'll just query G on all of these q points. Those are my actual queries. Okay. I'm going to somehow assume that because the total number of errors were at most 1/12, I'm going to hope that on this particular line, the errors that I see is at most 1/3. Okay, we will argue that with high probability this will be the case. Okay, but let's assume, suppose it was at most 1/3. I will run the Reed-Solomon decoder with error threshold 1/3. Notice that my distance was 1 minus 1 by 12 was I'm working with d by, I mean, d is at most q by 9. So I have a fair amount of room. So 1/3 fraction of errors I should be able to correct. I mean, if there were at most 1/3 errors, that is. Okay. So you decode to get a polynomial. In fact, when you get a polynomial, you get a unique polynomial because we are within the unique decoding database. But of course, I put in get in star because my assumption that the number of errors is at most 1/3, maybe that's wrong. Maybe the line I chose was such that on that line I got too many corrections. Okay, but I basically argue that that will not happen with high probability. Okay, and I just return g of 0 as my final answer because I mean the line is something I set up in such a way that at t equal to 0 it was taking value x. So that's what we're going to do. So this is the algorithm. You just choose a random, you shoot a random line through the point you care about, decode the Reed-Solomon code on that line, and answer according to that decoding.
So here the random line is given by you pick a random line.
Yeah. So pick a random line by picking u uniformly at random from fq to the m minus 0. Okay, that's your this thing. And on that line, you just query all the points and decode it. Now, the local decoding is much better if the m is much larger, because that means that your ambient space is of dimension q power n, but you're only querying q points. Right? So your locality gets better and better if the ambient dimension becomes larger and larger. Okay, that is, you're querying a lot less of the ambient space than compared to the block line. Okay, so what we'll do is we'll just analyze the algorithm. Analysis is actually very short. Okay, so let's define this set as to be basically this clouds, like wherever we had disagreements. Okay, so I'm going to define this set X to be the set of all A in FQ to the M, such that this G and the actual polynomial F disagree here. Okay, these are the set of disagreements. And I know that the size of S is at most 1/12 of Q to the M. Because that was the assumption that someone told us that this G agrees with F at a lot of places. Okay. Now, what I want to know is, suppose I pick a line L at random through X. Okay, or maybe I should call it LX or something. So you pick a random line through X. I want to know what is the expected fraction of L intersection S over Q. Like how many of these bad points do I expect to see on this line?
Then you were taking a random line.
Okay, so now let's ask ourselves, fix a specific point y. Okay, and I want to know, does this y, what is the chance that this y shows up in this line x? Sorry, this line lx. Well, for that to happen, I have to choose this unique line between passing through x and l. Sorry, x and y, right? I mean, that's the only time that y will show up. Which means, if I look at this line and look at all points other than x, by themselves, they are uniformly random points. Because every point has the same chance of showing up in this line x, in this line x. Okay, so if I had ignored the point x, this is like saying this line is sampling q minus 1 points from the ambient space. Each of them, like marginal on each of them, is independent. So the chance that every single one of them may have shown up in S is at most 1 by 12. Right? The only catch is that the stupid point x is not random. Every other point is like a uniformly random point. The point x alone is not random. Okay? But nevertheless, that can add the number of bad points by at most 1. Right? Because that's just contributing 1 point among q points on this line. Okay? So I will let you verify that this is at most 1 by 12 plus 1 by 3. 1 by 12 because you expect this line to basically sample the same fraction as the number of points in S that we have in the ambient space. Because every single point is other than x is uniformly random. But maybe the stupid point x that I chose was actually a point in S. So that will always be an extra 1 that is added, but that's only 1 among q points. So I get a 1. Yeah, okay. So this is 1 by 12 plus 1 by 3. So we assume that q is like at least what, 36 or something? Yeah, we assume q was at least 36. So 1 by 12 plus 1 by q is at most 1 by 12 plus 1 by 36, which I think is 1 by 9. Yeah. Yeah. So this is like almost 1 by. So this tells
This is the 9 which appears in D.
sorry?
This is the 9 which appears.
Yeah, this appears in that D because I wanted to make sure that okay, good. So this is what we have, and now I want to. So this is the expectation of when I pick a line at random. What fraction of this line do I expect to be corrupted? Well, that is at most 1/9 of this line. So I'm now going to apply a Markov. So by Markov, okay, the probability that when I pick this line at random, that L intersect S is greater than 1 by 3 times Q is at most, I mean, it's at most 1/3 just by Markov inequality. Okay, so which basically tells me that in step 2 of whatever, step 3 of my algorithm, I assumed that my error threshold was at most a third. And this is basically telling me that my assumption is going to be right with probability at least 2/3. Okay, and because therefore the Reed-Solomon is going to work because the distance is sufficient for me at this point. So therefore, the whatever Reed-Solomon decoder with threshold 1 by 3 will in fact decode to f restricted to this line, because that will be the right restriction that it decodes. So which means that actually when the algorithm finally returns f hat of 0, it is going to be f restricted to the line L at point 0, which is the same thing as f at x. Okay. So that's it. So this is basically the analysis of the local decoding algorithm that we have for this. It's a very simple, it's a beautiful algorithm. By the way, I think this algorithm is due to Lipton. Okay, and yeah, good. So now, okay, we made a lot of progress, but we actually have 4 shortcomings. 2 of which I'm going to try and solve, no, maybe 3 of which I'll try to solve in the remaining time. The 4th one is the biggie, which will go to the next lecture. Okay, so here are the 4 shortcomings. One of the things I mentioned was that we don't want local decoders. We don't want local characters, we want local decoders. So I started off with some function. Somehow we converted that to a polynomial and we were looking at the evaluation of the polynomials. And the above algorithm was telling me how to correct those evaluations. It's not telling me how to compute the Boolean function correctly. Okay, so that is problem number 1. Problem number 2, though we haven't set parameters, it's unclear what is going to be, is that one of the things we wanted is we wanted the rate to be reasonable. That is, we wanted k prime, which is a block length after you do this encoding, to be polynomial in whatever block length you start off with. At the moment, it's unclear because there seems to be some exponentials that are showing up in, I mean, the block length is like q power n that's showing up. So we need to make sure that, that's not like crazy. So that's point number 2. Point 3 is that the alphabet is actually whatever, q or fq. Whereas what I finally want is a Boolean function there. So this thing is going to tell me that I start off with a Boolean function, and I'm now going to output a function that is like as if on every point it's outputting a large number of bits. That's not what we wanted. We wanted a Boolean function there. So that's the same thing as saying I don't want a code that is just in some random place or something. I actually want a code that is a binary code, which has the properties that I care about. And finally, whatever we did for 1 by 12, I eventually want to do this to half minus epsilon. I don't just want a local decoder that can handle 1/12th fraction of errors. I want a decoder that can handle half minus epsilon errors. Okay. So what we are going to do in the remaining time is to try and address 1 and 2 first. And because in fact, once we address 1, we'll be able to set parameters and 2 will be evident from there. And then focus on 3. Okay, and I think by the time we won't have much time, and 4 is going to be a larger thing, which we will defer to the next one. Okay. Now, let's address problems 1 and 2. So to begin with, I actually had a function f on 0, 1 to the small k. It was a function on 0, 1 to the small k, which is the same thing as a string of things in 0, 1 to the capital K. Okay. Now I want to somehow convert this into some Reed-Muller code word. That's what I want to do. I want to take this message and then somehow build a Reed-Muller code word based on that. Okay. And ideally, what I would like is I would somehow want to do this, this conversion of the string f into the polynomial. Let me give it a polynomial name. Let me call it p. Okay. I want to do this conversion in such a way that all the coordinates of f somehow show up here somewhere. It's like embedded inside. So that's what we were talking about in terms of systematic encoding, because then local correctability of p will give me the local decodability that I want. So that's what we are trying to do. Okay. And so the way we are going to do this is I'm going to choose a certain specific set of coordinates, which I will call capital H, whose job is to act like this set capital K. Basically, that's where it's going to get embedded. I will identify the set K. I'm somehow embedded based on that. So what we will do is we will choose some subset of FQ such that the grid corresponding to this set H basically has size capital K. Because that's where I'm going to plug in the actual values of F into those locations. Okay, that's the systematic encoding that's going to happen. So pictorially, H is like I have chosen some bunch of things here. So this is what whatever H power M looks like It's like some small subcube that is sitting inside. And it's just that we have chosen things in such a way that the size of this subcube is roughly capital K. So you come up with some one-to-one mapping to sort of say, if you care about the first coordinate, look at this. If you care about the second coordinate, look at this, blah, blah, blah. Okay, we will just choose some capital H with this size guarantee and work with that. Okay, and now here is one small idea which for people who have done algebra computation and so on, this will be trivial, but I'll just go over it in any case. Which basically says the following. Suppose you tell me that, look, I want a certain set of values to be taken here. Find me a polynomial that takes those values. Okay. And this observation basically says there is always going to be one polynomial whose degree in every coordinate is at most this side length. Maybe it's at most that side length minus 1. This is just standard interpolation. Like this is like, if I gave you h points and ask you to find a univariate polynomial, you will find a polynomial of degree h minus 1 that takes specific values there. You can just do that with m-variate things. It's just that degree in every coordinate will now be like h minus 1. Okay. Now this polynomial f hat is what is eventually going to be my p. Okay. So what did we want eventually? I wanted to make sure that given a Boolean function f, I construct a low degree polynomial p such that the values of the Boolean function is somehow embedded within the evaluations of p. So now what I have done is given I've identified the specific subcube which has the right size, put values according to f there, and I'm going to ask, give me the polynomial that takes these values at these places. That will give me something, some f hat or something. This f hat is what I'm going to call p.
So in this HM cube, we put only 0 ones, right?
Yeah, notice that these polynomials could potentially have taken values in f cube. But 0 and 1 are two elements in f cube. So within h power m, somehow it takes values only zeros and ones. Because I've assigned it based on what f is supposed to be here. Okay, but of course, that will force it to take maybe some values outside. Okay, so but nevertheless, that's what my p is going to. So if you think about what is the encoding is the following. I had a specific function f that told me what value should go here. But the fact that it is a low degree polynomial tells me what values the whole thing is supposed to be. And that whole thing is my final encoding. And we have set it up in such a way that it is systematic by definition. Like every value of f that you care about shows up somewhere on that subcube. So you just correct that according to what you. Okay, so this is going to basically solve the problem 1 part, which is the decodability versus correctability issue. Because now we'll think of p as the Reed-Muller code, like do all the correction there. If I wanted decoding a specific coordinate of f, that's the same thing as decoding a specific coordinate in h power m. Okay. So now let's just set parameters and convince ourselves that this is a poly-rate code. Okay. So just to put things in perspective, we started off with a function which was on small k bits. Okay. And we also thought of this as a string of length capital K. So what I'm going to do is I'm going to choose my h of size roughly square root q. I haven't told you what q is, but just hold on for a little bit. Okay. And I'm going to choose m to be something like k over log h, which is like k over half log q. Okay. And this is where the choice of q comes. In fact, you take q to be something like 81k squared. Okay, this k is what ties up with what this k is. So q is essentially like the arity of the function that you started off with. And the other parameters are also chosen depending on that. Is this okay? Is this what the final parameter assignment, etc. is going to be? And let's just compute stuff. One of the things I wanted was that the size of h power m, I want this to be roughly 2 power small k or capital K. Okay, because that was identification that was happening. And we just set it up such that this is basically size of h power k by log size of h. And this is log 2. Okay. A power k by log, this thing is just 2 power k. This is just 2 power k. And which is capital K. Okay. So one part of it is done. The next thing I need to get a sense of is the final block length is like, so firstly, what is a degree? So degree, notice that it, by the above definition, it was at most, whatever, it was at most h minus 1 in every coordinate. So the degree is at most m times h, like a stupid bound on that. Okay, and by your choice of m is actually smaller than k. Okay, so I'm going to say degree, whatever this d is, this is at most m times square root q. In fact, I'll put it as at most k times square root q. Okay, just because degree in every coordinate was h minus 1, which is square root q. And k is anyway bigger than m. So I'm just putting a worse bound. The reason I'm doing this is because notice that if you stare at this and this, you immediately get that d is at most q over 9. Because this is what we needed to make sure that our local decoding algorithm works. Okay, and because it's like 81k squared, 81k squared is bigger than 36 because k is at least 1. So that part also goes in. So the final thing we need to figure out is what is the block length. Okay, so the block length of a Reed-Muller code is you're going to evaluate it at all points on FU to the m. So the block length is actually q power m. Right? But this is nothing but the same thing as square root q power 2m. I'm writing it as square root q power 2m because we just calculated square root q power m. That was capital K. Because h was square root q. So square root q power m is just capital K. So therefore this thing is going to basically be k squared. Okay. And then finally, how is q related to all of this? Well, an alphabet size. This is equal to q, which we set it to something like 81k squared, which if I want to write it in terms of k, this is, I mean, capital K, this is polylog of capital K. So it's a very low alphabet sized code whose block length is certainly just polynomial in the original block length. And you get decodability, which is like 1 by 12. Okay, so this basically then says that you therefore now have an encoding where it is 1 by 12 decodable in polylog k time, because everything was polynomial in q, whatever was happening there, but q is like polylog in capital K. So the decoding time is just polylog k. Okay, the block length k prime that you eventually end up with is just k squared. Okay, so that's like just write it as poly in capital K. And the alphabet is also not very large. It's like actually just logarithmically large or polylogarithmically large in capital K. Okay, so great. So this basically solves both problem 1 and problem 2. The issue 1 was that we were dealing with local decodability. We wanted local decodability, but we were doing local correctability. This analysis basically puts the actual function into the code work. So local correctability gives you local decodability. That's number 1. And number 2 was that we wanted this to be an inverse poly rate code. So we have managed to get k prime equals poly in capital. Okay. So that solves issues 1 and 2. But of course, the issue 3 was that, well, I wanted a code over a binary alphabet. You are instead giving me a code over some slightly larger alphabet. this is equivalent to saying that if you give me a worst case hard Boolean function, I am giving you a slightly average case hard, but not something like a multi-output function. I'm not outputting a single bit, but I'm outputting a symbol from sigma. Okay. So can we get around the third part? So this is issue 3, which is I want to get a binary code. Okay. Again, so what I'm going to describe now is completely standard. There should be nothing surprising here. But let's just look at it pictorially. Okay. I started off with some message, which was in 01 to the capital K. I did some encoding. And then I got something in a larger alphabet, like what used to be bits here now became whatever, slightly fat symbols. Okay, it became each alpha I is some element of sigma. What I want to instead get is a binary code. What is one obvious choice you can do right now?
Encode into these symbols.
Yeah, that's right. So what we are going to do is we're going to come up with some function which I will call the inner code. Okay, whose messages are actually symbols. Okay, and each one it's going to, I don't know, return it in 01 to the small r, something. It's going to encode it using bits, using maybe r bits. So what we are going to do is we will define this new code, and let me call this as whatever the encoding one, the original encoding function you had, and this new code, which is encoding one with encoding inner. I mean, it's written this way, but it's called the concatenated code. But don't think of this as, I mean, it's actually the other direction, right? You first apply encoding one, you get alpha 1 through alpha capital alpha k prime, and then you apply the inner function on each of those coordinates. Okay, so but it's written as a concatenation. This is basically going to be this nth inner of alpha 1, blah blah blah, with nth inner of alpha k prime. But each of this looks like a block of length r, but interpret this as a large symbol. I mean, like as in, I mean, I'm going to interpret this as a string in 01 to the k prime smaller. That is, like, think of them as separate letters. So this gives you some function. It gives you a different code with the same message space as earlier. But now your output is now a Boolean string. Maybe length is a little larger. What used to be have block length k prime now has block length k prime times r. Okay, but if your inner code is also nice, maybe this k prime times r is something that you don't mind. You don't mind having.
Would it be like something here to use like field size to Q prime?
Yeah. So the point.
Don't use the inner code at all.
So the point is, I mean, like we don't like. It might be the case that you have a slightly different thing with a lot of errors, but every error looks like you're only changing one of the coordinates. Some of the way you count distance is a little different.
Yeah.
So I mean, I guess your thing is like if you imagine that sigma is like, let's say, this was f whatever 2 to the r.
Yeah.
You're saying why not just write them as bits themselves? Somehow the distance guarantee doesn't quite work out. It may be the case that the code has good distance when you're treating it as something over sigma.
Okay.
But when you treat it over bits, it doesn't have good distance because you could sort of like you could only make k prime errors by just making one error in every block. But that amounts to corrupting all k prime symbols if you're thinking about it from sigma's perspective.
Okay. So in this setting,
yeah. So which is why you just do an inner code so that even if there is a single corruption, that also percolates as a lot of corruption. Basically, that's what the inner code is really doing. Okay, and this is a very simple lemma, which is that, and in general, this is true about concatenated codes, and you will have that in the problems that I'm still building. Which is that if your outer code and inner code are good, they have some nice properties. Turns out this concatenated code actually continues to have those properties. Okay, so here is one thing that we are going to use here, which is that Suppose the outer code has some delta 1 decoder. This could be local, this could be global, I don't care. Some delta 1 decoder. It has some guarantee if you promise me that there are at most delta 1 fraction of errors. The inner code has some guarantee that says that if there are at most delta 2 fraction of errors, I know how to decode it. Okay? Then this concatenated code actually gives you that same guarantee that as long as you promise to me that the number of errors is at most delta 1 delta 2. Okay? And here is the proof. So let's say you are given a received word. This is a received word. Okay, so this has with at most delta 1, delta 2 errors. Okay, so I'm going to think of this as blocks of size R because each of them is supposed to be whatever I had gotten after the inner code, and each of them is like whatever I had gotten after the inner code, etc. etc. So now there is an obvious decoding algorithm. What is the decoding algorithm you do? You start with this. From this, decode this to alpha 1, decode this to alpha 2, blah, 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 decode this to alpha whatever, k prime. Now apply the older thing. Of course, it could happen that some of these decodings fail because there's just too many errors that happened in that block. If that fails, I will just put a random thing there. Okay. Now, what do I want to argue? I want to argue that as long as you promise to me that there were not more than delta 1, delta 2 errors, I want to say at the end of this decoding process, at most, delta 1 of these alpha i's are wrong. Because then I know that the outer code word will actually decode it correctly. Okay, so how do I argue that at most delta 1 of them? Well, this is just a simple listing. So just notice that at most delta 1 fraction of the blocks have greater than delta 2 fraction of errors.
Otherwise, total error.
Yeah. Which means at most delta 1 fraction of these blocks will get decoded incorrect. Which means when I eventually find out alpha 1 to alpha k prime, at most delta 1 fraction of these coordinates are actually different from the actual code word. But that the outer decoder will now take care of. That's it. Okay. So therefore, a corollary is that if you now take the Reed-Muller code and you concatenate it with the Hardness code, okay, because Hardness code had a local decoder where that delta was like something like a quarter. Okay. Previously, I had a 1 by 12 coming from the Reed-Muller code. So if I concatenate the two, I now get a binary code of with whatever local decodability of something like 1 by 48. It's like 1 by 12 into 1 by 4. So I get 1 by 48. The only thing we need to verify is that how did the block length become? Because Hardness code was a terrible code. Right? Because it was stretching something of k symbols to like something like 2 power k symbols. But fortunately, we are applying the Hardness code on tiny things. So it creates a larger stretch, but the stretch is something I can absorb in. Because the alphabet size was just like so the point is the Hardness code, what will happen? So it will, I should maybe have written it here. The Hardness code that I'm going to be using is something that should map sigma to 0, 1 to the something. So every symbol, I'm going to think of it as a bunch of bits. Maybe it uses something like R bits. But if I use R bits, it will get mapped to 0, 1 to the 2 power R. But that's the same thing as saying it gets mapped to 0, 1 to whatever size of sigma. So that is, it takes a single message and returns it to like a vector whose length is the number of possible messages. But fortunately, the number of possible messages was just polylog in capital K. That's what I'm going to incur on extra thing. Previously, it was k squared. Now it's going to be k squared polylog k. That's a big deal. Okay, so that's why all of that got absorbed into this. And because sigma was polylog k, that's the extra that I'm going to end up incurring. So therefore, now you have a locally decodable code, which has inverse polynomial rate. It has all the local decodability that you need. By the way, notice that because the symbols are so small, you don't even need efficient decoding for Hadamard. You can actually do a brute force there. Those symbols are so tiny that you can afford to run a brute force computation on those symbols. So there's nothing fancy that's going on. You're just coming up with some way of converting that whatever, something over alphabet sigma to something over alphabet zero. Okay, is this okay so far?
So we are applying the Hardware code as the inner code.
As the inner code.
So the property that we want from that
Hadamard code is that I want there to be a quarter decode. Let's say a quarter minus epsilon decode.
yeah, and the message should be sitting inside the code word.
So that will continue to happen because like whatever was the old message, I mean like when I go from alpha 1 to here, this alpha 1 shows up here anyway.
Oh, okay.
Right, so Hadamard code was also a systematic code. The Reed-Muller code also we set up in a systematic fashion. So whatever was the old thing that we want, it continues to be embedded inside this thing. So everything that we want happens. Okay. And now finally, we have the corollary that we were claiming, which is that it now gives us some way of going from worst case hardness to average case hardness. Because what are we going to do? Suppose someone gives us a function small f with the guarantee that it is worst case hard for size 2 to the delta k. There is no circuit of size 2 to the delta k can actually exactly compute the function. It has to make a mistake somewhere. Now, what are we going to do? We are basically going to construct this f tilde. And what is f tilde? F tilde is Reed-Muller concatenated with Hadamard applied on f. That's what f tilde is. Okay. And because k prime was polynomial in capital K, we know that small k prime is like order of like small k. And therefore, you now have that, if you, oh, sorry, I should not have written 1 by, this should have been 1 by 48. Yeah. So now you get that, if your function was worst case hard, get some average case hardness. You know that no circuit can make fewer than 1 by 48 sort of errors. And the new circuit size will now be from some 2 to the delta prime of k prime, because you will have to now incorporate the time taken for the decoding process. But yeah, but then because 2 to the delta k is like so large, maybe the delta becomes a little smaller, like big deal. Okay. So that is the okay. So this is the part that I sort of wanted to do. I'm surprised I finished this early. So we basically get that sum from worst case hardness, we get some form of average case hardness. Okay. And see, let me just stop here. So basically, because there's no point starting the next this thing, I can maybe give you a hint as to why you need a notion of list decodability. Because the point is we need to get to something like half minus epsilon hardness. Now, which means there's no way you're going to be in the unique decoding regime at all. There's not even going to be a unique code word that is within a distance of half minus epsilon from what you started off. Right? Because even if your code space had 2 strings in it, and then suddenly your distance is like at most half, which means your unique decoding radius is like at most a quarter. So asking for a decoder that happens to work with half minus epsilon number of errors is just too much. So that's why you need to relax yourself to list decoding. You can't do unique decoding anymore, we'll do list decoding. But everything needs to happen locally. Okay, and that's the tricky part. Like, what do you mean by local list decoding? You care about a specific coordinate. And you want to know, in the possible corrected code words that are close to the received word, what all values can this coordinate take? And if I just tell you that the values are everything in sigma, that's a really silly way of giving local decoding. So you need to somehow prevent me from giving just that effort, because that could actually be the right answer. Like maybe it is the case that the list size is bigger than Q. And maybe there is a different polynomial or different code word that takes those values. But nevertheless, we need to come up with a definition that sort of addresses the problem that we have. And what we will basically show is that the Reed-Muller code is not just locally decodable, it is actually locally list decodable. with not just error 1 by 48 or something, you can go to error 1 minus something. And then it will turn out that the Hardness code is also list decodable. It was unique decodable for quarter minus something. But it will turn out to be list decodable at half minus something. So if you concatenate the two, that gives you half minus something. So that's what will eventually happen. So Reed-Muller will be 1 minus, Hardness will be half minus, and then together will give you half minus. So that's what we will do in the next lecture. So one minor thing, the next lecture we will not have on Thursday because I guess 2 of the people are not going to be around at least. So we will meet 1 week from now. So next Tuesday, whatever that date is. Yeah. Okay, great. So let me stop and
The local list decoding, they came up with it. I mean, this was the reason people, or it existed before that.
I don't think it existed before that. I think it was introduced by Madhusudan, Lokatranesan, and Salibalan. By the way, the previous thing, it went from worst case hardness to this hardness. And then there was this thing of what is called the Zor lemma. And it's a very powerful tool. It's like saying, suppose you have a very biased coin, a coin that shows up heads with probability, I don't know, 90%. Now you want to use this to simulate a rather unbiased coin. Okay, so what do you do then? And the trick is usually that you just toss the coin 10 times and take the parity. Okay, and you can just show that it actually goes down exponentially in terms of the number of tosses that you're going to have. And intuitively, the thing is, if I ask you to guess the result of K, the parity of these heads, even if you manage to have some side information for 9 of the 10 tosses, like if you knew exactly what the 9 of the 10 tosses was, but only you had some uncertainty about 1 of the tosses, that's enough to completely mess up the parity. So this was used to basically say that if you have a function that is reasonably hard, you build this new function, which is the XOR, which is like saying you compute the function on K different, like I don't know, K was used, let's say, I don't know, L different inputs, and take the XOR of the answers. And that's your new function. And they basically showed that this function is significantly hard. So that's how it went. You went from 1 by 50 hardness to significantly hard. And then you could go apply this on it. That was implausible, except that the standard Zor lemma, this K blow up becomes a little too much. So they have to do something called the de-randomized Zor lemma to make sure that this K becomes order K. But nevertheless, everything works out. This was the original proof. So SCE said, no. Actually, Reed-Muller code actually gives you everything. You just needed to come up with this definition of list decoding, local list decoding, and it just works out. Yeah. Yeah. Okay. So let's meet next week.